This is an MEI conference session that I did in 2013, and I decided to think about pictures that have inspired me to think differently about topics that I thought I understood in core maths. The way the session ran was that every few minutes I put up another one of the 20 pictures, briefly explain why I liked it, and then the 40 people there discussed it between themselves, what they thought of the problem, what they thought of the insights, and how they might use it in the classroom. The first problem was I created this in response to the frustration I had that I felt students used to think that when they saw a picture of a graph and the equation, they didn't fully appreciate what the link between the two was, and that the equation was simply a label for the graph. So here we've got a variable point xy that is allowed to roam up and down that line in the first quadrant. Now it might look, this is a bad diagram because it might look as if that dotted line is perpendicular to the given line, but that's not the intention. So we calculate this area, the small triangle that is sitting on the x-axis, we calculate the area of this triangle, and then we calculate the area of the whole triangle. And when you then add the areas of the two smaller triangles together, clearly you get the area of the big triangle, and the equation that results is the equation of the line. So very dynamically the students can then see that the position of that point on the line didn't have to be the one given, it could be anywhere in the first quadrant, and that equation is always true. So for me that is a very dynamic understanding of what the equation of a line is all about. Of course then you're left to think about what happens if that point goes into other quadrants, but that's an interesting process to go through. And then what other curves might you have where you can get this kind of insight into what the equation is all about. So this is completing the square, and completing the square in schools is often taught in a very procedural way. You've got to half the coefficient, we get 1x squared, you half the coefficient of x, and so on. And that completely ignores the fact that what you're doing is completing a square geometrically. Now at the end of this, when you get x plus 3 all squared equals 100, then of course it's natural to think x is 7 because we're talking about a physical square, and x being negative doesn't really mean anything, and that doesn't concern me because I want students to understand the structure of completing the square. And then of course we can return to the world of algebra and realise that x is negative 13 could be a result of an abstract algebraic equation. But splitting that initial rectangle here into two bits helps them to see why it's useful to halve the coefficient of x, and then also pointing out in the final equation x only appears once, and that's really the point of doing completing the square, because then we can rearrange easily. I often find that students and teachers introduce the formula for things like the sum of an arithmetic series far too early. I think students need time to think about where the formula comes from and not just see it algebraically. So the link between this picture and the equation at the bottom is clearly that the number of red dots is 3 plus 5 plus 7 plus 9 plus 11. That being half of a rectangle, you can then see what that would be. 5 by 14 rectangle, and it's half of that. We then ask students to think about, for example, what's the sum of all the 3-digit numbers that are multiples of 3, and they can see that, well, they can get there, it's 102 all the way up to 999. They can imagine the top row of their rectangle would have 1,101 dots, I think it is, and then they'd have to really think about how many rows that rectangle would have before halving the product. But they then got a sense of where this formula comes from, at least a full lesson before they ever see a formula. Infinite geometric series, here the idea is that I've got a 2 by 2 square which I'm going to divide equally between 3 people. So after quartering it, because quartering is easy to do by folding or whatever, I've then got the problem of we've got 3 people, red, blue and yellow, but the bottom right hand square, that final quarter has got to be divided again, and carrying on the process indefinitely leads to the result that a third, clearly yellow gets a third of the whole share. A third is going to be a quarter, plus a quarter squared, plus a quarter cubed, and so on. So it's insights into infinite geometric series through pictures. An interesting question to ask there is which other pictures give similar insights? Can you do anything with equilateral triangles or regular hexagons or anything else that will help students to understand certain geometric series? The laws of logarithms, log A, B being log A plus log B, is often thought of in the context of A and B being specific numbers. And it's interesting to think about what happens if one of those A's or B's turns into an X, and it makes you think differently. It makes you start to think about graphs. Now, when I first see log of 3x as a graph, I think of a transformation, and it's a squash towards the y-axis, a factor 3, but then I look at the graphs of log x and log 3x and it looks like it's been a vertical translation. And of course it's that as well, because the log graph has that property, because of laws of logarithms. So it's bringing together translations and the laws of logarithms, and then asking the question which other graphs have a similar property that a transformation in one kind of transformation is simultaneously a different transformation. This is a screenshot from a GeoGebra file which is generating in the bottom left hand corner the graph of the function g of f of x, and so m is a general point on the first curve, top left curve, and then the coordinate at that point is bounced off the line y equals x to turn the y coordinate into an x coordinate, which is then fed into g of x. And it's interesting to look at the coordinates of the 4 points. You know, if point M has got coordinates a comma f of a, what are the coordinates of the other points, and why does the graph that you get at the end equate to g of f of x? But there's other interesting things about that, because clearly the final horizontal line shows you that the range of the composite function cannot be greater than the range of g of x. And similarly, if a number is not in the domain of f of x, it cannot be in the domain of the composite function. So although it's very important to do all this algebraically, I think graphically gives new insights. And there's also perhaps something to think about here in terms of if you were to differentiate the composite function and think about maxima and minima, how does that tie in with in this case, maximum and minima of g of x? So there's something there about the chain rule, which is often done in a very procedural way, to think about that graphically. The question here started by asking those present to vote for which had the greater area of the two. And of the 40 people, I think 2 people decided that they would be the same, and then the calculations take over, and in fact they are indeed the same. At a formula level, this is obvious, because both have half times 7 times 5. You need to think a bit why it's half times 7 times 5 for the sector of the circle, but nevertheless you get a symmetry in the two formulae. But what's much more interesting to me is why. Why are these two things the same at a geometric level? And perhaps the best way of dealing with this is splitting up the sector into an increasingly large number of smaller sectors and seeing how each of these approximates to a triangle where the sum of all the bases of those triangles is 7. So it's a precursor to calculus. In this diagram we've got the graph e of x reflected in the line y equals x, and its tangent is also been reflected, as is this handy little gradient triangle. Now we know from y equals e of x that its gradient is equal to the y coordinate at that point. When you reflect it, that 3.67 as a y coordinate on e of x becomes an x coordinate on the inverse function log of x. And of course this 3.67 in the gradient triangle appears over here. And now, playing around with this for a short while, thinking about what's the gradient of the red tangent, it's going to be 1 over 3.67, 1 over the x coordinate that we've used, and therefore the gradient function of log of x is 1 over x. A very surprising result the more I think about it. This, I think here is one very good example of where technology really made me think differently about mathematics. I knew from my school days that if I differentiated sine 2x, I would use the chain rule, out would drop 2 cos 2x, and I would move on to the next question without really thinking what was going on. At a transformation level, sine 2x is a squash, as shown, the red graph on the curve. Now, when you've done that, this means that in order to get from 0 up to 1, it's got to do it twice as quickly. And the gradient everywhere on that curve is twice what it was originally. And hence, you get this doubling. That's where the first 2 in 2 cos 2x comes from. It's linked to that transformation. And then the cos 2x is clearly the same periodicity as the graph sine 2x. And I wonder how often we could think of the chain rule in terms of transformations. The surprising result from A-level A2 core is that when you integrate 1 over x, you get natural log of x. Why on earth does that happen? At AS core, it's the only thing that we integrate every power of x except for x to the negative 1. And we leave that one out. So it's a natural question to ask, before you've done anything on exponentials possibly, what is it? Maybe that's the way to start A2 core. And we don't know what the answer is, so we stick it into some GeoGebra file and we gather some data. The idea here being that the slider bar dictates the right-hand limit of this region, the left-hand limit always being 1, and we ask the software to give us some data, and we notice things like the area between 1 and 2. If you double it, you get the area between 1 and 4. Or if you add together the area from 1 to 2 and the area from 1 to 3, of course there's overlap in doing this, you get the area from 1 to 6. And so you start to think, well, this is a lot like logarithms. So maybe the integral has got something to do with logs of some base, and then the question is what base, and it all amounts to thinking, convincing yourself that the base is going to be when the area is passing the value of 1, and hence natural logarithms arise. This problem arose quite harmlessly once when a group of teachers were thinking about y equals x sine x, and one of them threw away the comment that the turning points would be the same as they were for sine x. Natural thing to think, maybe. So we drew it. They convinced themselves that the graph could not stray outside the regions contained between y's x and y's negative x. And then we thought about if the maximum point was at pi over 2, well, you substitute pi over 2 into y equals x sine x, and you get y is pi over 2 as well, so that's the point where it's on the line y equals x. Now, if that was a maximum, that means a little bit to the left. That x sine x graph must have gone a little bit above the y equals x graph. And that's impossible. We know that because sine x is always between negative 1 and 1, and therefore it can't be greater than x. X sine x can't be greater than x. So that meant that the turning point wasn't there, and in fact you then start to think, where is the turning point? And actually at pi over 2, when the curve touches the line y equals x, that's where the line must be tangent to the curve. Now here's a good example of where the technologist told me I never understood the maths in the first place. So at school I would be able to use a substitution. In this case, what would it be? U is x squared over 20, and then my limits change, and I've got something I can then integrate, and I can evaluate the definite integral. I didn't ever stop to think what's going on at a graphical level, and you can see that the graph of this ugly function on the left is shown below it, and the more pleasing graph, 4 plus sine u, is shown on the right. The limits have changed, so the region is going to be a different width, and then the shape is changing as well. And how on earth, at geometrical level, has the area managed to stay the same? I'm not claiming here that they look the same to the human eye. I'm saying that they are the same if the scales were if the scales on the two were drawn perfectly. So at a graphical level, what's going on in terms of transformations that ensures that we're not going to interfere with the area of this region? I think that's quite interesting to think about. Here it's a nice link between binomial theorem and infinite geometric series. When I look at an infinite geometric series, AR squared and so on, I'm thinking in the world of A and R being specific numbers. But you put A equals 1 and R equals X, or negative X, then I get an expression which is the infinite series that starts like this at the bottom, and I start to think of graphs. And I know that this infinite series converges to A over 1 minus R, so I draw that graph as well. And then I can see that if it's not between negative 1 and 1, the things are not going to be the same. That's interesting. But also that if I choose any point between negative 1 and 1 on the x-axis, and look at the two corresponding red and blue dots, well, the red dot is where my series is converging to, and the blue dot is how far I've got after just a few terms. And it's interesting to look how it does very well near 0, and it's taking its time as you approach x equals 1 or negative 1. But seeing that graphically, we've got an infinite number of geometric series corresponding to points with the same x coordinate there. There are lots and lots of different ways of showing the double angle formulae. This one, well, certainly some, if not this one, is taken from Roger Nelson's books, Proof Without Words. There are 2 books. I don't know if this one's in there, but it might well be. And here we've got AB is the diameter of a unit circle, P is the general point, and, well, it's only, I'm going to be drawing it over here somewhere, but P, of course, is P, we've got a right angle, and this 2 theta by circle theorems is double that. And it's quite clear that these two lengths are sine 2 theta and cos 2 theta. But if you then chase the angles round, the lengths round, you then can express lengths PP dashed and OP dashed without referring to the 2 theta and just using sine thetas and cos thetas, and you get the double angle formulae. For example, in the biggest right angle triangle, the hypotenuse is 2, so this length must be 2 cos theta, and then that will allow you to say that AP dashed is 2 cos theta times cos theta. So AP dashed is 2 cos squared theta. If you take off 1, you've got cos 2 theta. And there's lots of other ways of thinking about those. Okay, the compound angle formulae, again, lots and lots of ways of proving these. Here's just one. It looks a lot like a way we might prove Pythagoras lower down the school. With Pythagoras, the red and blue triangles will be identical, and here we're saying that as we rearrange those shapes within the same outline, the same rectangle, then putting the 2 blues and the 2 reds together, we can see that the area of this rhombus here must be the area of these 2 squares. And a couple of steps later, you've got the identity at the top. This is one where, again, if I ever had to solve d(y) by dx is x plus y, of course that would be further maths because you can't separate the variables. Then I would just have to do the standard routine. But you type that into autograph and you get these lovely tangent fields, which then make me stop and think what's going on. And what this is saying is that you take any point in the plane and you're interested in the curve that passes through that point. Well, all we know about it is its gradient at that point is the sum of its coordinates. So, for example, if I want a point that passes through 2, negative 2, I know the one thing I know about that curve is that its gradient there must be 0, because x plus y is 0. And then when it leaves that point at gradient 0, it's heading somewhere else, its coordinates have changed, and that's dictating how it behaves from there on. And do try putting that into autograph, because it's interesting to see then how autograph draws the curve without knowing what its equation is. It doesn't work, it doesn't do the calculus, it just follows the tangent fields. And here you can see two different starting points, and they give 2 very different graphs. So I chose 2 points very close to, let's say, x is negative 5, y is about 4, and by varying it ever so slightly I get 2 totally different graphs. So there's almost an idea of chaos coming in there. This was an MEI maths item of the month a few months ago, well, a few years ago now. A teacher at Tunbridge School sent this in as a curiosity and said, you put that into autograph, you get a straight line. And indeed you do. And it's interesting to think why, because it doesn't have the general y equals mx plus c formula. And what's worse is that if you think about negative 1, put that into there and you do get 1. So there's actually, as well as that line, there's an isolated point over here. If you think about x plus y equals 1 and cube both sides, then you're starting to get something a lot like the equation that you've got, with a bit of work still to do. More interestingly, in autograph, change that 3 to a k and alter k, and you see the situation here where k is 3. Either side of k is 3, interesting things start to go on down here. This is the ambiguous case, the sine and cosine rule. The slider bars in GeoGebra here dictate an angle and 2 sides of a triangle, and of course you can imagine that as the angle at BAC increases, there will be a point when it's a tangent to that circle, and so then you would have a unique triangle that satisfies the properties given. And it feels as if you've got to be very precise to get a unique triangle given these 3 bits of information. And that's if you imagine changing the length, the slider bar that dictates length BC, the radius of that circle will increase and decrease. And at the moment, when it's a tangent, then you've got another special case of a kind of a unique triangle. But you don't have to be that careful, because there's whole infinite families otherwise if you think carefully about this. And I think the playing with the GeoGebra file then helped me to understand what was going on with the ambiguous case. And to try and explain that a little bit better, just imagine that you let AB get much smaller, keep the other 2 the same, and then you can see there's a whole infinite family. As soon as AB is shorter than BC, then you've got a unique triangle. So you've got these very special cases and then these infinite families. This is the difference of 2 squares, and it's the difference of 2 squares physically. The big square, which has got 3 colours at the moment on the left, you take away the little b by b square, rearrange it, and you can see where that formula comes from. And the difference of 2 squares, the very wording of it suggests that there's ways of doing that are not algebraic, and yet I very rarely in school see anybody do anything with this idea that is anything other than algebraic. It's very interesting to think at a numerical level. When can a prime number be the difference of 2 squares? And then you're starting to think about factorisation of algebra and factorisation of number. Last one of the 20, possibly my favourite. If you actually work out all these lengths in this unit circle, where that's theta, and chase the angles around, you will see they're all labelled correctly. And I think, first of all, that's interesting, seeing that tan can be thought of as a tangent to a circle. But all sorts of other things come out of this. Identities. Look at any one of the 5 right-angled triangles in there will give you, using Pythagoras theorem, you'll get a trig identity. And there's other ways of getting identities too. If you think of the area of triangle ADE in 2 ways, half base times height, in 2 ways. The second way, the base being ED and the height being BA, because of course they're perpendicular, then you get another trig identity. And because this is a screenshot of a dynamic file, if B is allowed to start close to the x-axis on the circle, as B then starts to wander around that first quadrant, you look at what's happening to these 6 lengths, and that gives you insights into the 6 graphs. And you can see things like why, for example, cosec theta is never going to be less than 1, and all sorts of other interesting things. What happens when theta is getting very close to 90 degrees? What's happened to the length BD? Okay, well, that's all 20. If you look at the MEI website and follow conference links, you will see all these resources there and more. I hope that's been helpful.